Hello everyone and welcome to this lecture. In the past lecture we saw what are contours and we said that contours will be important when we deal with the topic called contour integrals. So if you recall, a contour was a piecewise smooth curve in the complex plane. Now we want to define something called a contour integral. So let's say you have a function. You have a function of complex variable as f of z, and then you also have a contour on the complex plane. So let's say this is my contour. We denote it by C, and this is the complex plane. Obviously the contour can be either open or closed, or it might intersect with itself at some point, and there can be many variations, but let's consider this simple picture. And let's say you have this function f of z on this complex plane, and now what you want to do is that you want to evaluate the following quantity, and this quantity will be known as the contour integral. So let's say we want to evaluate or calculate an integral that looks like this, that is, you have f of z dz. So you are taking the function and you want to integrate it, but you can see that there is this c over here. This means that the contour that we are choosing in the complex plane. So this is similar to a line integral that you know from vector calculus. So these type of integrals are known as contour integrals. That is, there is a contour in the complex plane and you have some function, and then you want to evaluate the integral of that function along some specific contour. So let's try to motivate this contour integral through an example that you already know from your high school physics, that is work. Obviously it's not the best example, but it should give us some motivation. So it's a motivational example. So let's say there is some force like this, a resistive force or something like that, and you want to know the amount of work done. So if you recall, that work was defined as some force, that is, which is representing this function f of z times dx, right? This was for the real variable, but since we are now in the complex plane, so let me just write this thing is for real variable case. And if you translate this whole thing into the complex variable or into the complex plane, let's say this will be f of z dz. And let's say there are many paths. Let's say this is a contour c1, this is a contour c2, there might be a contour c3, and this value of w will depend on the contour chosen over here. Let's say you have these three contours, and by ci I mean I can take values like 1, 2, 3, and w1 will correspond to c1, w2 will correspond to c2, and w3 will correspond to path c3. So this means that this quantity that you are interested in, that is the work, is dependent on the path that you choose to evaluate. So that's why we want to deal with these contour integrals. and in the next video we are going to see some examples on how we can evaluate some contour integrals. So before I finish off, again I want to remind you that this is the main thing you need to keep in your head, that this type of integrals, whenever you see something like this, small c under the integral sign, you have to understand that this is a contour integral. That means it will depend on the path you choose to traverse in the complex plane. So this will be it for today, and I'll see you guys on the next lecture. Thank you.